Okay, so let's talk about the second part of two-dimensional random tomography. But I want to detour to discuss a bit about principal component analysis and its challenge. In particular, what's going on and what we encounter when we have a high-dimensional data. And remember, when we talk about data analysis, in particular high-dimensional data, high-dimensional is a very, very important feature that we have to respect. Okay, so this is a kind of a 10 minutes lecture, so I hope to finish it in 10 minutes. I hope I can do it. So, null case first. And the main target and the motivation is for this paper. We want to handle two-dimensional tomography from noisy projection. And remember, this is the data we get. Noisy data, and we want to recover the projection direction of each projection images so that we can apply inverse X-ray transform to recover the underlying image. Okay, and this is in part 1 we have discussed it, and in part 3 we will handle the noisy data. But we need to discuss principal component analysis before we can do so. And now, recall PCA, when the covariance matrix is none. This is very important. We start with assuming that the covariance matrix is none and discuss what PCA is. Let's consider a random vector X. And it's a p-dimensional random vector. And its mean is mu, and the covariance matrix is sigma. And this definition is very standard and simple. Now, we consider the following quantity. We want to evaluate U1, which is the max of the variance of UTX, and U is known one. What does it mean? It means that we project X to U. We project X to U. Oh, shoot, we project X to U, but because it's variance, so you have to subtract the mu. Expectation, it's a second moment of U transpose X subtract U, mu. That is what we want to do. And this guy is written in this way. If you do an expansion, this is X minus mu transpose UT U. And if you write this guy, this is what? Because expectation is linear, you move it inside, you get U transpose T, sigma U, and U is 1. And the solution U1 captures the most variability of the data called the first principal component, which looks like that. Suppose those blue dots are the data set. Mu is the expectation. U1 is the first principal component. And how to get U1? Very easy, right? Maximize this guy is what? Finding the top eigenvector. Finding the top eigenvector. Easy. You can continue and ask if you can find subspaces, d-dimensional subspaces, and those vectors are orthogonal to each other, and maximize this guy. And you can see that the solution will be the top d eigenvectors and eigenvalues. And remember, sigma as a covariance matrix is always positive definite because it's the outer product of the matrix. It's a data matrix in the end. So you capture the most variability of the data in a d-dimensional subspace. And UI is called the ith principal component. Okay, and this is a picture. In this two-dimensional picture, the most variable direction is this one, and the second most variable direction is the one that is perpendicular to it, fulfilling this condition. So this is the second principal component. So that is PCA when the covariance is none. But in practice, what do you really know? You don't know mu. You don't know sigma. You can estimate mu by mean, right? Which converges very fast. So we don't worry too much about it. But what about sigma? What about sigma? Right? And similarly, if you want to find not only the first top principal component, but the subspaces spanned by the top B eigenvectors. Similarly, you do not know the covariance matrix. You need to estimate it. But estimating covariance matrix is in general a challenging mission, in particular in a high-dimensional setup. Let's take a look at one example. Very simple random vector, which is Gaussian, and all the covariance are 1. And if the covariance is 1, you can imagine if you can recover it well, what will be the distribution of all eigenvalues? All eigenvalues will be very close to 1, isn't it? Because identity matrix has all the eigenvalues 1. But now, suppose we sample only 10 points, IID from X, and you estimate the covariance using the sample covariance. That is what you get. Okay, and you evaluate the eigendecomposition. This is the distribution of all eigenvalues. You see, 1 is what we expect. But really, we get many things that are close to 0 and even 3. What's going on? That looks weird, isn't it? Okay, maybe it is because you only sample 10 points. 10 is too small, so that you don't get anything reasonable back. Maybe that's a reason. Okay, so let's take a closer look. Now, this time I take more points, 20. And this is the result. Still, you get 2, 0.5. 20 is still too small. Let's get more points. Very good. Now I have 2,000 points. Right? It's getting closer and closer to 1. Very good. But what about if you have 2,000 points, but dimension is 1,000? In this case, you see, hey, the distribution of eigenvalues, again, you see something very close to 0 and something very big, even close to 3. And even the histogram can be well approximated by some function called Marcenko-Pastur law, which tells you that in high-dimensional setup, 1,000, even if you have 2,000 points, 2,000 is kind of, you can say, big, but it's not big enough. Okay? But its scale close to the dimension of the data, then you run into some troubles. Okay, so this is a high-dimensional noise model that we want to explore and to see what's going on. What's going on in the previous simulation. Suppose we have IID sequence X, Xi in RP. Mean is 0, covariance is sigma squared. Easy. Okay, but now we put one assumption. That is, assume there exists some gamma which is in between 0 and 1. And let's say, define Cn to be n divided by p, and the p is p over which goes to infinite. Okay? As n goes to infinite, you see this Cn will be in between, it will be non-zero. That is, Cn converges to some value that is non-zero, but in general you don't need to take limit. Whatever, it just says that p depends on p of n, in particular when n goes to infinite. In this case, the dimension p and the sample point n, they are linearly related. And this is sometimes called the large P large n model or high dimensional model. In this model, we want to study what's going on of the eigenvector and eigenvalues of simple covariance matrix. That will be the mission. And the Marcenko-Pastur law, under this very simple setup, we will have more complicated setup later when we need them. Suppose you have you consider x, which is x1 up to xn. You have this is a random matrix, and the p and the n will satisfy what we discussed before. Simple covariance matrix is defined in this way. And we assume we know the mean is 0, so we even don't need to do a subtraction. Just consider this. And then you run eigendecomposition. And you define a measure. And this measure is called empirical spectral measure or empirical spectral distribution. That is, for all eigenvalues, lambda L, you put that delta major at lambda L, and you sum all of them divided by P. So this is a major. Okay, and now you have some observations. You know XX transpose and X transpose X have the same non-zero eigenvalues. So in this case, we just consider P. P is less than or equal to n. Otherwise, you will see some degeneracy because they have the same non-zero eigenvalues. If P is greater than n, you may have more eigenvalues, but all the extra eigenvalues are 0, so you get some delta majors loaded at 0, blah, 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 all these kind of things. So to simplify the discussion, we just assume P is less than n without loss of generality. Very good. So what the theory tells us we have about Marcenko-Pastur law is the following. Suppose P depends on n, so that P divided by n goes to lambda. Okay, in between 0 and infinite. When n goes to infinite, then mu n will converge this empirical density function, imperial spectral distribution will converge to a major called mu weak, which is major satisfies this guy, looks like this guy. And this looks very complicated, but this is not terrible at all, because what you see is if lambda is greater than 1, meaning that P is greater than n, and as we discussed in the previous slide, you will have some extra 0 eigenvalues. So you generate eigenvalue, you generate 0. Okay, eigenvalue at delta major at 0. And all the others are 0, 1, and this nu has the distribution function like this guy, which has the picture like this. And this is the Marcenko-Pastur law. And you can precisely write down 2 boundary points, which is lambda plus and lambda minus, and its morphology can be fully quantified here. So this explains what we saw before numerically. When you have 2,000 points, 2,000 points in 1,000 dimensional space. Okay, and that is the null case. What is a spike model? Spike model is a non-null case. That is when you have sigma. In particular, what we will discuss later, and many of the future applications, we will run into this kind of model, saying that y is x plus c, where x, okay, we understand it as not as a signal, is a random matrix with low rank covariance. Okay, and the c is a random matrix with IID entries. And we will assume x and the c are independent, and we have all these conditions. Expectation of x is mu, covariance is sigma, is of low rank. But c is the noise, which has mean 0 and the covariance sigma squared IP. And again, we always assume, considering P over n goes to gamma, is positive. And that is what we call spike model. Spike, what is spike? What is a spike? Spike are those low rank stubs. Those are called spike. Or sometimes we call it a large P or a large n model. Under this spike model, what we know is, well, recovering the eigenvectors and the eigenvalues, in particular for the low rank structure that we have interest as signal, is actually very challenging. We cannot achieve it. Suppose C is white, that is, you have IID entries, and the C and X have finite force moments. Everything is fine, perfect. And even we assume lambda L is simple. Then this is lambda L and LK, the sample eigenvalue and the same sample eigenvectors converge with probability to the following. Sample eigenvalue will converge to the population eigenvalue, but it is perturbed in this way. You see, you get lambda k plus sigma squared, 1 plus gamma, sigma squared divided by lambda k. When lambda k is greater than sigma squared times square root of gamma, hold on, do I use gamma? Let me check. Yes, I use gamma, correct. I use gamma, so this is the gamma. This is gamma here. And if lambda k is small, smaller than sigma square times square root of gamma, then you get sigma square times 1 plus square root of gamma. And what does it tell you? It tells you that if the eigenvalue lambda k of the covariance matrix we have interest, that is this guy. I forgot to mention, I have to write sigma k, sigma to be summation of, I use lambda L, lambda k, and then I use UK transpose, and the k is from 1, I use D is low rank. Okay, I forgot to introduce this notation. That is the sigma, this is the covariance of X, and which we view as the signal part. Okay, in this setup, suppose sigma has this eigenvalue decomposition, and lambda k is the population eigenvalue, uk is the population eigenvector, and small l k is the sample eigenvalue, and the u hat k is a sample eigenvector. Then the sample eigenvalue and the population eigenvalue has this relationship. What it tells you is if the population eigenvalue is small, how small is small? When it is smaller than sigma squared times square root of gamma, then, sorry, you don't get any information. You get zero information about the true eigenvalue. But if the eigenvalue is sufficiently large, it's larger than sigma squared divided by square root of gamma, then actually you can get some information about the population eigenvalue. And this lambda k, when it converges to this guy, you see this is kind of a quadratic equation of lambda k. So you can solve a quadratic equation if you know sigma squared and you know gamma, right? Then you can recover lambda k from LK. Okay, but if the eigenvalue is too small, then sorry, you don't get anything. Moreover, the eigenvector, the sample eigenvector and the population eigenvector, their angle actually converges to 0 if lambda k, the signal strength, is too weak. But if the population eigenvalue is sufficiently strong, then you get something deviated also from 1, not really 0. Ideally, if you can recover the true eigenvector, then their inner product should be 1, right? Because you recover the precise eigenvector. But it tells you that, sorry, no. If the signal, if the strength is too small, then actually you get, with probability 1, totally perpendicular result. Not orthogonal, no, sorry, not in parallel, but totally orthogonal. That is the result. The eigenvector you get is totally garbage. But when the eigenvalue is sufficiently large, like lambda k is large, then you get something, but it's deviated from the true eigenvector. You still get some deviation, and this deviation will become smaller and smaller when lambda k is getting larger. For example, when lambda k is going to infinite, you see this one goes to 0, this one goes to 0, and you get 1. Right? And when lambda k is going to infinite, the same. This guy goes to 0, right? And you get lambda k plus sigma squared. So if, again, when lambda k is sufficiently large, very, very large, and you know sigma squared, you just do subtraction, you can recover lambda k from LK. Okay, so overall, what you get is a biased eigenvalue, and you can recover it because this satisfies a quadratic relationship. But for eigenvector, sorry, we cannot recover the eigenvector. It's still a big open problem, how to correct or estimate eigenvector F. And this is the structure of PCA. Under a spike model, we have to respect. It is biased always. And later on in the next lecture, we will discuss how to leverage this structure to design an algorithm to denoise the two-dimensional random tomography database to achieve the two-dimensional random tomography solution. Yep.